Can you hear me? Hello? Hello?
Yes, sir.
Can you see the screen? Oh, I
No,
have
sir.
not shared it. Can you see the screen? Hello?
Yes, sir. Yes, sir.
Okay. We have only 2 weeks left. I don't know, only few students are present. I do not know what they're heading for. They are thinking they will pass in topology. I don't know what your friends are thinking. It is my last semester. I don't have any problem to give lot of F's or D's. Okay, I won't complete the proof, but I already gave you that stone bias test students of that. Okay, so let me explain that. I have given it from Royden. Actually, I was looking for a good proof of that. Okay, well, first of all, ये जो Royden किताब मैंने बोल रहा हूँ, ये एनालिसिस मैंने 3rd edition बताया. Actually, 4th edition is also available. Indian edition is there. And ultimately, if you want to learn, this book is good in a sense. Usually, if book goes for 2nd edition, itself shows it's a good book. Usually, the books do not run after 1st edition, and this book has got 4th edition. But 4th edition, of course, Royden is not alive. It has been done by somebody else, Fitzpatrick. He teaches in University of Maryland, College Park. It's a good university, good in both physics and but many areas: physics, mathematics, electrical engineering. University of Maryland, College Park, because it has got 2 campuses. College Park is a better campus. He got the 4th edition. In fact, 3 areas: basic, real analysis, including measure theory, including measure theory. Topology, one set topology. Function analysis. That you can learn from this. In fact, if you are interested in any one of them, you should read this book. So, book is popular throughout the world actually. So, because I already told you it has gone to 4th edition. In fact, certain books, if you have not, while a student of mathematics, if you have not read from that book, people won't consider that you have learned that topic. Royden is such a book, classical book, that if you claim that if you know some good analysis or function analysis, then they will say whether you have looked at, you know Royden, have you studied Royden. So you should look at Royden. And I am telling you why I have given this from this book. And 4th edition, this person did. This is the practice that good book, the publishers ask somebody whether they can revise on that. And Fitzpatrick here, I would like to tell you that if you go for 4th edition, you go for the acknowledgements in that. There you'll see that one Indian's name. Himanshu, it is written this way. Actually, I think the Professor Frederick didn't know that. It should be Himanshu. Yeah. Okay. Actually, he did his BTech MTech in electrical engineering from IIT. And I taught him several courses in math, including measure theory, probability. I taught him several courses. So he went there for PhD. And I think he was sitting through his course. And of course, he made many suggestions for them. The acknowledgement is for reading the manuscript of that. And he did. And that's why acknowledgement is there. Himanshu was very good in math also. Okay. So this is one Indian name is there, and I taught him several courses. And also I told you that it should be actually this. The book is so popular you should read, and why I have chosen to pick up from this thing is that I already wrote that stone Boy stress theorem problem is that many books, many well-known books, including Rudin, they give what is apparently wrong proof. Reason is like what I said that Alipranthi's Barkinsaw, when we were reading that, second lemma. Again, I am telling you, lemma 11.2, page 58. Here, they are taking point A and then doing for each x. The previous lemma they are using, but x has to be not equal to. That means, what? How do you handle it? That is the problem with the proof, that you are taking the union of this thing. The point is that when x equal to a, then your argument doesn't hold. So that's the proof is wrong. In fact, you do not need lemma this way. Actually, I know from where there is a book for introduction to functionalism, Goffman and Petrick. They picked up from this. It's a good book, Introduction to Functional Analysis. And only they were giving the algorithm of the proof. So they have sliced the proof of giving this book into several pages, like lemma. But lemma 11.2, again I am telling you, read that. But when x equal to a, then there is a problem. So that, and then their theorem 11.3, they are proving. Here I am telling you, this theorem is correct, but their proof is wrong. Reason is because they are using this wrong lemma. In fact, this statement of lemma can be changed on that. It should not depend on a point. The moment you go for a point, the whole proof will crumble up. Whole proof will crumble up. Okay. So that's if you fix a point, that's the problem. Okay. So that here, but I'm saying lemma 11.4 is a different thing. That is obviously true. And the theorem 11.5 they are proving that is correct because they are using this. So that point is that ultimately, how do you go for a correct proof of this? Correct proof of this. Okay. That's the thing is that where you look at. So that's why I was looking at several books, some papers also that I mentioned, the Stone's original paper. Actually, not original, nice, simpler version of his paper. Original paper is 1937. But later on, he published something for Mathematics magazine. But paper is heavy, but I think you will understand. And now, thing is that I found that Royden, I read the proof twice to ensure that he has not made any mistake. So I am not giving you the proof explaining. So you should read. Okay. Particularly you should look proposition 30. This is actually third lemma of Ali-Francis working set, proposition 30. Proof depends on this page 211. I have posted it. So that in fact proposition 30, he has given the proof after lemma 31. Look, lemma 31 is the first lemma of Ali-Francis working set. Means they call it lemma or proposition of that. Lemma 11.1. Proof of lemma 11.1, there is no problem. So this is lemma 31. So, but then of course you should rate that how they're avoiding that trap. Okay. But here the point you see that they're taking one point outside a closed set. So there you just look lemma 32 statement. Look how they have avoided that kind of thing. They're clearly saying it is a point not in a closed state. That how they're avoiding it. Okay. So that you should read actually proof of proposition 30 depends on this lemma. And it is not difficult. Okay. And lemma 33, here let me tell you that. They have proved for the polynomial this function, that it can be approximated by polynomials. Whereas Ali-Francis working saw they did with this, but that's not a problem. Okay. So that Ali-Francis working saw that lemma will work for this. Okay. Whether you take this or this, it doesn't make a problem. Okay. For proving this, that it can be approximated by sequence of polynomials, you see that what they are taking binomial series. Okay. So that after that theorem 34, they are doing, you can prove that. So basically, you need this. Don't forget. Okay. So I read it twice. I didn't find any mistake. Okay. So that if you want a correct proof, better you go for that. And also, this is proof. The whole proof is sliced into pieces, so that gradually you know that what you are doing. So that you should do it. In fact, what I say it is to a Stone in his paper in Mathematics magazine that he has a different proof, but that is also an easy proof. But again, the problem is how to avoid fixing a point at that. When if you want to fixing a point, you should know that in your proof, you are sure that what I'll say that your proof works. That says x equal to a. This case is not coming. Okay. In Radens it is not coming. Okay. Their proof is entirely different. Okay. That you should look at that. How the proof, so that lemma 32, and then you look at the proof of proposition 30. That how they are proving it. Okay. Right. So I won't recommend the proof from the Ali-Francis Barkinsa, but I am telling you the results except lemma 11.2 they are true. Theorem 11.3 that I am saying, telling you that's the lattice version, that is there. This is proposition 30, the proposition 30. Actually, it is a proposition 30. Is Ali-Francis Barkinsa theorem 11.3. Here they have taken less condition than the lattice function space. Okay. Let it be a function space. Function space means you have a vector space of functions and as well lattice. Okay. In proposition 30, you see that they have not taken actually vector space. So look at the conditions 1 and 2. This is less than a vector space. Though it is lattice property is there. Okay, lattice means maximum and minimum should be there. Now, these three problems you should do. Let me tell you. any length is Barkinsa, you tell Sodavan that problem 96, 97. These are all applications. Problem number 6, I'm not giving too many problems. Problem number 6, 10. 10 is a difficult problem. It is your choice, option. I haven't given the example, but you can think of that. You read the problem. Okay, problem number 10. And but problem number 12 and 13. 13 they have given hints. Okay. 13 is a special case of 12. So make sure you do it. It means here they are saying, look, I said I need Stone-Weierstrass theorem gives nice dense subsets. Nice dense subsets. Now here in problem number 13, what they are saying, suppose X is a metric space, compact metric space. In Stone-Weierstrass theorem, we are doing in the compact topological space. We are taking suppose compact metric space, then Cx D is a separable metric space. That means we are getting a countable density. Is a separable metric space. This is the result. In fact, converse is also true. That means if you just take a metric space and suppose this is separable, this can be proved this is compact. It can be proved actually. Okay, this is compact. Okay. In fact, problem 12 they have treated a special case. They have taken X is a subset of R, which is compact. Okay, that means closed and bounded set by Handel what they did. And then the general case. X is a compact metric space, then Cx is a separable metric space. But converse is also true. That means if Cx, suppose Xg is a metric space and Cxd is a separable metric space, then it can prove that X has to be compact. But you don't need to bother about that proof of that, but at least this much proof you should do it. They have given hints, that's actually enough hints that of what kind of countable sets you will pick up. Okay. First of all, compact metric space, you know that has to be separate. So that's why they have taken that. Let X be a countable dense subset, and then they are giving Fn, defining. And now look that they are taking the algebra generated by that. Similarly, what you say, vector space generated by a set, generated by a set. Similarly, algebra generated by a set. You know how will you express as a linear combination of that in terms of the elements of that. Similarly, you can have this. Though here it will be intersection of all vector spaces containing that, and here it will be intersection of all algebras containing that. Of course, you are working inside an algebra in Cx. So that is algebra generated by that. So that algebra generated by you are taking that, then it is coming. But of course, it need not be counted. But then you will have to look at that. Here the game is that function is the next semester you need that. Suppose here over real I am doing it. Okay, so that here actually suppose you have here take this. When you take this, suppose you have a vector space over real. Okay, now look, see that. This can be approximated by each of them can be just rational numbers. So that if you take all these things, rationals, now over rationals, we choose. I'm taking here something countable, vectors. So if we take this thing, alpha I belongs to Q, okay, and N belongs to N. Suppose this is countable. So you will have to show that any element of A can be approximated by such elements, so that ultimately a countable dense set will be there. You should work out that. Again, here I should work that this you take with the rationals. Okay, I think last semester I told you that set of algebraic numbers is countable. How do you show that? If you remember the proof, same way. So ultimately you have to find a subset here, countable subset, which is dense in A. Since A is dense in CX, so this will be dense in C. So this will be countable. Here I should tell you that one thing that I Stone-Weierstrass theorem to go for, instead of real value, if you take this, the linear space of complex valued function, not real values. Some people to indicate the difference, they take this. This way they say it is real value. But in Yan, if you write if you write complex valued functions on X, then the Stone-Weierstrass theorem, under the condition that word has been stated in Royden on this, the algebra words. Okay. Theorem 11.5 or Naliprantis-Perkins or Royden, proposition 30. Basically, not proposition 30, that is the last theorem 34. This is Royden. Here you need to put, if you have complex valued function, you need to put one condition, that whatever algebra you are considering F belongs to A implies a bar belongs to, it is closed with respect to the conjugate. If the conjugate function means a bar means this. Okay. So a bar, X is a function, so X to C. So this is a function. So this is X. Don't confuse it. This is different. F bar X means this Fx, the conjugate. It has to be there. The algebra you are taking, that has to be closed with respect to the operation of conjugation. Then Stone-Weierstrass theorem is valid for complex valued functions. That Stone also did for that. Okay. And if it is not true, you can give a counter example that it need not be dense. It need not be dense. So this thing condition I am telling you. Complex valued function, it won't follow ditto. You need this condition. Without this condition, it is not true. I think if you are enterprising, don't think about the only examine that. Think about whether you can do it. That counter example. It's not very difficult. That if you don't have it, then you need not be other conditions of the real if you have, still it will be dense. Okay. So that make sure that you do it. Okay. Now let me tell you that. So I leave it and do this, and then you should do the problem. Now I will come back to this because I will need to really start connecting this. But I have posted, I think, two nodes related to metric spaces, related to compactness. Okay, so let me talk about that. Okay. Now look, different types of compactness. This node. sure that you read that. I will give in-class exam offline. So make sure that you read that. You don't need to mug up. You should be familiar with the arguments, different types of compactness. I have another interest in offline exam because I would like to see your faces. I'd like to know you personally. I'd like to meet you. Okay. Now look here, different types of compactness, recall that. Other than compactness, main thing is we have countable compactness. It's countably compact. And sequentially compact. You know that every open cover has a finite subcover here. Lindelof, I am not coming here, bringing it here. Every open cover has a finite subcover. Here every countable open cover has a finite subcover. And here every sequence has a convergent subsequence. Now look, I'm not going to prove all these things up there. Now thing is that countable things, you have countable, here also sequence. So that when you are dealing with this, sequence will play a role, and countable thing will play a role. And sequence by nature is countable. And already you have seen that if your space is first countable, then many things we can characterize through sequence. That's why first countable is playing a role in that. And here a subsequence, okay, here subsequence. Subsequence is not a problem. Subnet, I said that there is a problem. Not a problem in that. It is a sort of what is the better definition. Now the subsequence is subsequence. Now look. And cluster of sequence. Some people call it limit point, but I won't prefer that, or accumulation point of a sequence. Many people use limit point, but I do not prefer to use it because students confuse between limit of a sequence and limit point of a sequence. So cluster point of a sequence. Cluster point of a sequence is, informally you can say that many members of the sequence gather around this point. Suppose you are starting with Excel, formal definition you can see that. Different types of compactness in definition 1. I said what is frequently means. That is a frequently, and then cluster. Extend clusters at X. Okay. And here basically means that many members of the infinitely many members. Infinitely, informally, infinitely many members of the sequence Xn gather around X. When say infinitely many members, it will only happen that frequently. That I have given the definition. That what does it mean, the frequently? Okay. Basically, whatever m you will give me, always I will find any neighborhood of that. Given any neighborhood of X, and given any number m belongs to n, I will find n naught belongs to you, where n naught for some, n naught. Now you choose next n naught, for n naught same neighborhood, will get another bigger number that n naught such that it will belong there. So this way go on. So that means you'll get infinitely many members. That means frequently it will be there. In other words, frequently. Frequently and infinitely is basically the same thing. So that means but it's not. After a while, all the members are gathering around. That I'm not saying. After a while, all the members. I'm saying infinitely many members. That means what is frequently? Frequently. So frequently, I said that the sequence xn is said to be frequently provided in A. I have given started with the set A, but eventually 100 over. Look, I have to take a sequence in a topological space, not necessarily metric space. And I took a point here and take a set here. So I'm saying xn frequently I have defined frequently in A. That means infinitely many members should be in A. That means whenever you give me some m, I will find n greater than m such that xn belongs to. So for okay, that is frequently. Now actually for cluster point, we take it. It has to be true for all neighborhoods of x. That means nx. A belongs to nx. That means given u belongs to nx, that's the neighborhood of x, and m belongs to n, there exists n, what n not equal to, such that n not greater than m and xn belongs to xn not belongs to. In place of a, I am taking u. So for cluster point, it has to be, that means if xn, the sequence is frequently in any neighborhood of x. That means xn, if xn is frequently any neighborhood of x, then we say that, then we say xn clusters at x. Some people write this way, cluster, not convergence, cluster. Okay, make sure that you just don't use arrow. If you just use arrow, it means convergence. But if you write cluster, it means cluster. Okay, so that, but this has, how you get that it will be, you can, so cluster points. So that now, so you given a sequence xn, it's a topological space, and I have defined, and x belongs to x, defined xn clusters at x. Okay. Now the thing is that how it is related to subsequences. That means, is it okay? Now the thing is that exactly that. Before the cluster, you see that in the real line, if I take this matrix, which is a topological space, then look, you have got two cluster points. Infinitely many members in any neighborhood of this, infinitely many members in any neighborhood of this. but it is not doesn't converge. Okay, but you have got a subsequence you could get converging to this, another subsequence converging to this. But why is happening? That you did last semester in metric space. Metric space, look, the way we have argued that this is can be guaranteed if x is tau is first count. It is not necessary, but it is sufficient. First count. Cluster point like this. That means I would like to have a result that xn. I would like to have a result clusters at x if and only if xn has a subsequence converging to x in x. Look, if you have this, then it will be cluster. That's not a problem. But there is the other way. If you have cluster at x, then you will have this thing. This is the problem. Okay, this way it is not a problem. This will be always true. Okay. Now look, if that's the theorem I have given, theorem 1. The first countable space is a sequence, then xn cluster at x, if and only if I have said there is a subsequence converging to that. But look, in the first part, when I am saying suppose there exists a subsequence, then I show this is a cluster point. There I am not using first countability. So that's why I am saying this will be always true. Because intuitively seeing infinitely many members should be there. That will be it will ensure. But only this way you need first count. Make sure that I have given the proof of that. Okay. So that actually one way you need that, and also you need that how we pick up a sequence in a first countable space. That remember that. First countable space, if you have this point, any point has a countable local base, but also you should understand that means n belongs to n. This is very important in your proof. Suppose it's a local base at x, I can also assume that for all n. Because reason if it is not true, then take Vn equal to this is finite intersection of open sets, so it will be also neighborhood of x. Each of them contains x. So then Vn will have this property. Then Vn n belongs to n is a countable local base at x, and you have this, and you'll have to pick up the sequence at, because if you pick up this xn belongs to n plus 1, that will be also in Vn. That will ensure that your sequence xn is converging to x. Look, in metric space, that will ensure it this way. This way you ensure that, because there so that's the way. The same thing, what technique we did, that will follow in that case. That I said that there is a local base even at x such that this decreasing. Okay, so this is very important. First countable ultimately tells you that you can characterize in terms of the sequence. That's why if you want to characterize in terms something in a arbitrary topological space in terms of sequence, very likely you need first countable. Okay, so that's the indication. And that countably compact, again I have seen that. Okay, the definition I have given. The theorem 2 I said that is immediate. I proved here that if x tau is compact, if and only is both countably compact and Lindelof. Now let me talk about this finite intersection property. This is not only important in topology, it is in measure theory also and subcode set theory. Finite intersection property. FIP. Some people write this. I think Conway has written this big. Some people write this FIP or finite intersection. That I want to explain that. Finite intersection. In fact, I said just it is not only important in topology, it is important in measure theory, set theory. Measure theory actually there is that you are doing basically introduction to measure theory, elementary measure theory. There is an area which is called topological measure theory. This is one of my specializations. That's why you don't wonder that I talk about measure theory, that means I talk about analysis, I talk about topology, topological measure theory. This means that you starting with the topological space and then there you have also a sigma algebra. Sigma algebra. So that essentially this is a topological space as well as a measure space. And then you need to have the interaction between topology and measure. Then it becomes a topological measure theory. Okay, right? Well, so that important. Then what is finite intersection property? Okay, so let me explain that. What is finite intersection? Suppose you have a set X that I want to explain, and suppose you have I belongs to non-empty set, of course. Each AI is non-empty. It is a non-empty family of non-empty sets, so that I is also non-empty. It ensures that you are taking a non-empty family, non-empty set. Okay. Now, finite intersection is why it is required. Intersection property means it pick up any finite set from here, any finite set, any finite subset of the index. Then if you take this, that means suppose j equal to ik, then it is non-empty. That means if you take any finite subfamily, their intersection is non-empty. Then it is called the finite intersection property. If U prime is a, here I have taken U and this E prime is a finite subcollection. I avoided index it. I have taken this. Then this is non-empty. U belongs to U prime. Here I have taken this. So this is actually, you should understand, subfamily of power set of X. Because each member is here is a subset of X. Okay, and for U prime is a finite subcollection, and that intersection is non-empty. Okay, right? Got it. So this is finite intersection, but definition is not very complicated. Okay, right? So this is called finite intersection property, but it is very important relation to compactness also. Okay, so that look, first example I have given that where it is doesn't have finite intersection property. That means you have taken this look here. Now why we are interested in finite? Here it has finite intersection property. You has but if you take the whole intersection, that means this is a standard notation. That means it means this is phi. right? Now what are here I am getting finite intersection property, but entire intersection is empty. Now the question is that suppose in what kind of space you have the topological space, that suppose it has finite intersection property. Does it imply this? Not empty. Because finite intersection property means every for finite sample is non-empty. That's it. Okay. This is. But this subfamily will depend on this. Here, if you have compact, and if you take family of closed subsets of X, family of closed subsets of X, then if it has finite intersection property, it has to be non-empty. It has to be non-empty. It's a very important condition. Now look, let X tau be a topological space, then X tau is compact if and only every closed subsets of X, every family of closed subsets, if and every family. Okay, so that what I am doing is, so finite intersection property means only for finite, any finite subfamily you take intersection will be non-empty. But the question is that entire intersection may be empty. Entire intersection may be empty. Okay, so that is the question. When do you see that? Okay, so now I have given a result here. Actually, I proved more general thing later on. That so theorem 3, I said we're starting with a topological space. So X tau is compact, not for every family, closed sets, because every compact subset is closed under the every closed subset of a compact space is compact. If and only if every family, not all closed sets, every family, whatever, of closed sets in X having with finite intersections and having FIP has a non-empty intersection. Every family of closed sets having FIP, this is important, has a non-empty intersection. Proof is easy actually. Okay. So I have left it as right now as exercise, but later on you'll see the proof of that. So here it means every family has a non-empty. That means if you take, suppose this F is a where each member of F is closed. F belongs to F implies F is closed. Every family of closed sets in X. So F is a family, non-empty family of course. Subsets of X. So F belongs to F is closed. And suppose F has, then F has FIP, finite intersection property implies the section F belongs to F has non-empty intersection. That is the meaning. To take easy, proof is easy. One way you see that if you empty intersection, then you will see that coming back. That just simply apply some basic rules of set theory. You will see that that will violate because we are taking compact. If you are assuming compact and if you are assuming this is empty, then you will get a finite family because of the cover, open cover. Remember that. F, then X minus F. If you have this is empty, then this will cover X. And each of them is open because F is closed. So it's an open cover of X. It will have a finite subcover. If you take finite subcover, now again you take complement, then for a finite subfamily, it will have empty intersection. So you get a contradiction. So you can prove it. So this is the important. Now look, I have given that for compactness, this is very important. Don't forget that finite intersection. Okay. Now, countably compact or Lindelof, countably compact, I have given that every countable family of closed sets with if I here every family, if I take countably compact, same argument, same proof, basically. Countably compact, then you'll have to take a countable family because countable compact definition I have taken starting with a countable family. So every countable family of closed subsets with Fi has a non-empty intersection. Okay, so if you can prove the previous one, this will improve. Okay, but if I go for Lindelof, that I have given. Okay. So for Lindelof, that what will be your idea that Lindelof, every open cover has a countable subcover. Okay. Not finite. That is the problem is here. That means finite intersection property you'll have to replace by countable intersection property. That I say. That means every countable subfamily has non-empty intersection. CIP. I have left as an exercise that you need countable intersection. Now try to formulate your own characterization. Okay. Now you see that theorem 4, you should read the proof on that. I am not giving the proof. I said now because this is has linked with your metric space characterizations of compact that I said prove that if X tau is countably compact if and only if every infinite subset of X has an accumulation point. So this way you do not need any other condition, only countably compact. Okay. But converse part, theorem 5, that you see that where I am using it. I need to ensure every infinite subset so that I need to ensure that when you're talking about accumulation point, so it intersects the neighborhood not only in one point, infinitely many points. That T1 guarantees. Let X be a T1 space and suppose that every infinite subset of X has an accumulation point, then X tau is countably compact. And here, theorem 4 makes sure that. I said, remember the minor exam questions. That's why I have given it that. You should read the theorem 4, read the proof. It is related to that minor question, exam question. Okay. But theorem 5, the converse, you need T1. So actually, unless you take T1, it need not be true. You can take trivial space, trivial topology. And X having more than one X is an infinite. Then you can see that it need not be true. Okay. This is actually compact. Only non-empty open set is X. So this is compact. But, so this is countably compact. But you do not have this thing. Okay. Then what is that? Every infinite subset X has an accumulation point. Wait. And I'm saying the thing is correct. Case 1, case 2, that you should do it. Still is a trivial topology. It will cover as a finite. It will cover. This is countably compact. This is not T1. No, this is every infinite subset will have an accumulation point. It won't work. It won't work. So let's think about it. Oh, I think you can think about it. Think about cofinite topology. on an infinite set. There it works. This is T1. Oh, this is T1. But not to make this is T1. So if it is not T1, then it's a problem. So you need to have a non-T1 space. So think about it. Okay, so I'm leaving it exercise. If star is not T1, then theorem 5 it not be. I may give it in the exam, so make sure that you do it. It not be valid. Right now, whatever I was thinking that it's not coming. In trivial topology, it's not coming. Point other than that will be true. Okay, so that this theorem 4 and 5 for T1 space is countably compact if and only if every infinite subset of the accumulation point. For metric space particularly it is T1 space, so it is true. That's the way actually we did. For metric space we didn't go for actual proper definition of countable compactness. We have done this. It is called BW compactness, Bolzano-Weierstrass compactness. So we went that. So that I have given the proof of that. You don't need to mug up this proof. Just read the proofs. Just see that whether you understand the technique. Okay. Right. Now, okay, I'm just coming back after 5 minutes on that. Don't go away in that. If you want to do well in the exam, and also if you need a recommendation from me. And I think next semester you should start applying to the US and that. Here, now I'm not going to give you the proof of that. But theorem 6 means I have proved that every sequentially compact space is countably compact. You should just see that how it proved. But for the theorem 7, problem with again the sequence of that. This countably compact doesn't have link with the look, it is defined in terms of sequence. It is not defined in terms of sequence. Okay. And there we have not got any characterization of countable compactness through sequence. All I got through an accumulation point, infinite subset. So that's why if you want to go for a sequential characterization, that means countably compact plus that I told you, the idea of first countable that to get hold of sequential characterizations, first countable. Into sequential. So metric space is a first countable space always. That's why in a metric space, countably compact, sequentially compact, they're always same. That is why you should see that metric space actually when we are having sequential characterizations, how much of it you used? Only basically first countable property. More often, while taking considering sequential characterizations here, that you should now at the end of the semester you should look at the sequential characterizations for any sequential characterizations. Actually, you needed first count. Okay, that was good enough. Though, if you are more interested, that was also sufficient. Necessary, there is something generalization of this first countable that is called sequential space. So I am not going into that. Okay, so that every compact space, the countably compact first countable is sequentially compact. Okay. But a sequentially compact space need not be first countable. That also you should understand. Only thing it is a sufficient guarantee that first countable is sequentially compact. Now the thing is that I just want to give the introduction. Tomorrow I will finish that thing, next quarter, net characterization. Actually, let me tell you that when I wrote this, that time I didn't intend to give the proof of the theorem 10. Okay, I have not given the proof on that theory in terms of the subletters. And okay, but I want to give the Tychonoff product theorem in that. I will talk about that. The thing is that when compactness, and in a metric space you have, then these are two sames, sequential compactness. That means compactness could be characterized in terms of sequence. That means if you have take a metric space, remember that. Is compact in Xt if and only if every sequence X and in A compact subset in Hausdorff space will have to close. In A has a subsequence converging to an X in, that means, so that problem is that it is not only sequential characterization compactness, we are having a subsequence. Okay. Now, suppose we have an arbitrary topological space and I want to characterize. I told you that actually I can go for the compactness of the whole thing, because I already said that if Y is a subset of X, then you can think of Y is compact in X, same as you can think of that Y tau Y is compact. Y tau is compact if underneath Y is compact in X, means compact with respect to the topology tau. Okay, so that while dealing with this, I can think of the compactness of that, the characterization of this, so that the thing is that I said that characterization of compactness through net, so that already I did that closer point continuity give the net characterization, so that if you have in your topological space, this topological space, add here net characterization. Okay. Here I would like to point out, I have talked about subnet and that, so I would, rather than I thought that later on I thought that it's better to avoid subnet. But look, actually compactness in a metric space, we could do it with cluster point. Compactness in a metric space, one can characterize through the cluster points of a sequence. Cluster points. In a metric space, a sequence has a cluster point if and only if it has a subsequence converging to that point, because it's first countable space. That's my theorem, theorem 1. So, but basically the basic idea is the cluster. The cluster point doesn't depend on the idea of the subsequence of that, though we have the characterization. Okay, so that even if I don't go for subnet, I can define the cluster point of a net. That's easier to prove, easier to define, sir, easier to define, so that I can characterize compactness. What I'm saying, the topological space through cluster point, compactness in a topological space, I can characterize. One can characterize through cluster point of a net. I don't need subnet. Okay, so that but cluster point of net definition will be same as cluster point of a sequence. Look how we define cluster point of a sequence. We took a sequence xn, x. Xn is frequent in every neighborhood of x, which means given a neighborhood u x and given m belongs to n, there exists hold on. Hello, তোর মামা কোথায়? মামা বাড়ি আসেনি তো? তোর মামা কোথায়? ওখানে ঘুরছে কোথায়? তুই এখন কোথায়? তুই অনুষ্ঠানের সাথে তোর মামা ফিরে আসবে, তোর মামা কি ওখানে থাকার কথা? আমি তখন পড়াচ্ছি, আমি একটু পরে কথা বলছি, ঠিক আছে? So there exists, hello, given n belongs to n, there exists n, sorry, there, there exists n naught greater than m such that xn naught belongs to u. Now look, if I have a net instead, so I have a net, that you know the definition, net. Suppose I am taking a net. What should be the definition? This is not a problem. So here you have a member of the net, directed set. So that means given what I should, given take lambda 2 belongs to, suppose this is lambda, directed set is big lambda. There exists lambda greater than equal to, that you know that partial order, if you take it, it's opposite, the meaning is there. Usually people write it such that x lambda belongs to this. Okay, so this is exactly the definition of class type. We are following in that. Okay, but don't talk about it frequently. But don't talk about, I don't know whether something is outside infinite or not. So or inside, that I do not know. That depends on the nature of the directors. Okay, so given u belongs to n, given lambda naught, the element of the directed set, I get this. This is called the class. If you have given for each neighborhood of x and for each element of the directed set, if you have this, then you say that x lambda clusters at x. That you say that x lambda clusters at x. Okay, right? And this thing, so this is important. Now you say I have got subsequence of characterization of cluster point of a sequence. I can do that. Cluster point of a net characterized in terms of a subnet. But the problem is that okay. But the point is that it is good enough for that characterization. So I want characterization of compactness through cluster points. But subnet, if you go, now look, if you go for subnet, okay. So the cluster point I did, then I have defined subnet. Here I will tell you that subnet, if I want a characterization cluster point through subnet, so I need to define what subnet should mean. So I have given the definition of subnet, but I have picked up the definition. Tomorrow I'll talk about this. Basically, Wheeler and Moncrief also picked up from here. But Wheeler's definition is a bit strong for subnet. Look, he is giving, first condition is giving strictly increasing, basically. Increasing function. Don't talk about increasing function. Okay. And second is giving in cofinal. Okay. So called. But he is putting two conditions. Here historically I am telling you that his first condition is a bit strong actually. Okay. So that, and whereas Kelly is one of the early J.L. Kelly. He was a topologist as well as a major theorist. J.L. Kelly, he has his definition of subnet is a bit different. It's a bit different. But Kelly got the idea from what is called known as Moore-Smith, two mathematicians. And it is written in his book, Moore-Smith Convergence, that is net convergence. The idea of the net was given by Moore and Smith. That subnet is a bit different, but the thing is that I want whether it characterizes, it generalizes sequence. And good thing, it also generalizes subsequence. This also generalizes subsequence. Okay. So that I do not have problem with Kali. But the problem is the good thing about Kali, this is since it is a bit stronger, it is a bit inconvenient to work in the practical field when you go for that. And since it is a bit weaker, so any subnet with respect to Willard will be a subnet with respect to Kelly, but not the other way. Okay, because Kelly has taken a bit weaker condition. But the advantage is that it is more useful. More places you can, more useful means more places you can use it. Okay, right? So that my suggestion is that tomorrow I will continue with that. That you read this thing subnet from Willard, what I have given here. Okay, I have given cluster point definition, it's fine. I have given the theorem that cluster point. In fact, the theorem 8 that I have given characterization of cluster point through a subnet. Even if you use Kelly's definition, still you can prove it. It's not a problem. Okay, it's not a problem. So I will tell you what Kelly's definition and that tomorrow. But that you will get, I have posted in an article on Nate. Read from there. You don't need to go into the deep. You just look at the definition of subnet. I think second page you will get it. Page 2. Just see that. And here, there in the footnote, the author has commented that what is the problem. So that good thing is that theorem 8 also I can obtain from Kelly's definition also. So that, and the second note that I have given the characterization compactness through cluster points. Okay. So that after that I have given the Tychono's product theorem. So in general product topology I want to define. So tomorrow I will continue, but I'll say that you don't need to mug up. Just look at this note, page 7, the definition of subnet, which has been taken from Willard. And then look at this note on the Nate, page 2, read. It says definition of subnet and the footnote. Okay. And theorem 8 will be still valid, whichever definition you take. So tomorrow I will talk about the next note, the Nate characterization of compactness and Tychonoff product theorem. Tychonoff product theorem is very important. Okay. See you tomorrow. Okay, bye.
Sir, Kundu sir, hello, Kundu sir, hello.